In this work, we present Miles, making imitation learning easy with self-supervision. Miles is an imitation learning method that leverages a single human demonstration to learn everyday tasks while requiring just a single environment reset and no prior knowledge. By leveraging the self-supervised data, Miles trains a policy that allows it to learn highly complex, precise, and dexterous skills, such as locking a lock with a key as shown on the video to the right. This way, Miles makes imitation learning effortless for humans. The most effortless type of imitation learning is that where the human invests the least amount of time to teach a robot a new task. In this case, that is providing just a single demonstration. However, existing methods that leverage a single demonstration for behavior cloning, while efficient, they suffer from covariate shift. That is, by the time the policy trained on that demonstration goes out of distribution during deployment, it has no way of returning back in distribution to complete the task. Instead, a common solution to this problem is to collect multiple demonstrations which are then used to train a behavior cloning policy. However, the majority of current methods require hundreds of demonstrations to train robust, vision-based policies which can be very laborious in practice. One other approach is to leverage imitation learning methods that use reinforcement learning. Such methods can learn from only a few or even one demonstration, but they still require a human to repeatedly intervene to reset the environment. And in addition to that, the random exploration component of reinforcement learning methods can make learning inefficient. As such, current imitation learning methods require significant human effort and time to obtain robust, vision-based policies. To address these challenges is the reason why we propose Miles. Given a single human demonstration, Miles collects data autonomously in a self-supervised manner that demonstrates to the robot how to return to and then follow the single human demonstration. However, unlike common behavior cloning methods, the self-supervised data collection replaces the need to collect multiple demonstrations, and compared to behavior cloning from a single demonstration, Miles does not suffer from covariate shift, as its data densely covers the space around the demonstration. Similarly to reinforcement learning-based imitation learning methods, Miles collects data autonomously, but instead of being guided by random exploration, Miles' data collection is highly efficient, as it benefits from self-labeled data that directly guides the robot back to the demonstration. Additionally, exploration can cause disturbances to the environment and thus requires repeated environment resetting. However, as we explain later in this video, Miles' self-supervised data collection procedure strategically shapes policy learning to be independent of such laborious environment resets. Consequently, Miles aims to incorporate the benefits of training behavior cloning policies with supervised learning on large demonstration datasets, with the benefits of autonomous data collection, similar to that of reinforcement learning methods, however, in the setting where only a single demonstration is available. Teaching Miles a new task is actually very easy, and it only comprises the following steps. First, a human provides a demonstration to the robot, and this can be done either with kinesthetic teaching or teleoperation. Then, the human resets the environment just once, and this is a trivial process that takes a few seconds, and this is all we need in terms of human effort for Miles to start collecting data to learn a new task. Then, the robot begins to progressively collect augmentation trajectories in a self-supervised manner that guide the robot back to the demonstration. That is, several augmentation trajectories are collected for the first waypoint in the demonstration, then for the second waypoint, and this process continues until either we have collected enough trajectories for all the n demonstration waypoints, or certain criteria have been met. Now, as follows, we describe how an arbitrary augmentation trajectory is actually collected in practice. Now, assume that the robot is at the arbitrary waypoint shown in this figure, so just above the lock, and the gripper is holding the key. Initially, a random pose is sampled to which the robot moves in a straight line, so it moves away from the lock to this purple pose shown here in this figure. Then, the robot attempts to go back to the waypoint in a straight line. And as the robot moves back to the waypoint, we record end effector poses, force feedback, and RGB images captured from a wrist camera, as shown here in this figure. And the end effector poses are used to automatically determine the actions by computing the relative end effector movement between consecutive time steps. It is important to note here that as the robot attempts to move back in a straight line, the resulting augmentation trajectory might not necessarily actually be a straight line. If the motion occurs only in free space, then indeed that trajectory will be a straight line, but if this is not the case, then collisions with the environment may shape the robot's trajectory to be a more complex, curved path due to our use of an impedance controller that makes the robot compliant to its environment. After the robot finishes collecting an augmentation trajectory, we check for two validity conditions, that of reachability and that of an environment disturbance. If the reachability condition is violated, the augmentation trajectory is discarded from our dataset, but the self-supervised data collection continues. If, on the other hand, an environment disturbance is detected instead, data collection stops. We provide more details on the reachability and environment disturbance conditions in our paper. After collecting the augmentation trajectories, we fuse each augmentation trajectory with the remaining demonstration segment, following the demonstration waypoint to which each augmentation trajectory returned to, as shown in the figure in this slide. This way, we automatically create a new dataset of demonstrations that show to the robot how to return to and then follow the single human demonstration. After the self-supervised data collection finishes, Miles' policy is obtained as follows. In the scenario where no environment disturbance occurred during the self-supervised data collection, a network, and in our work an LSTM, is trained using standard behavior cloning on the new dataset of fused demonstration and is deployed in a closed-loop manner. If an environment disturbance actually did occur during data collection, then the LSTM is trained on the dataset of fused demonstrations, where it learns how to solve the task up to the state that has been achieved at the demonstration waypoint, where the environment disturbance occurred during data collection. Then, at deployment, the LSTM is deployed to solve the task up to that demonstration state, after which the remaining demonstration trajectory is replayed in an open-loop manner to solve the remaining of the task. So this is how we obtain Miles' policy and how the self-supervised data collection behind Miles works. Now, as follows, we show some of the examples of the tasks and experiments that we performed as part of our evaluation in our paper. Here we see Miles performing tasks that are contact-rich, that require dexterity and precision, which all of them are learned from a single demonstration and approximately 30 minutes of data collection. Such tasks include locking a lock with a key or inserting a USB to a USB hole. Here we observe Miles' performance on 3 other everyday tasks that are not contact-rich but still require dexterous and delicate robot manipulation, such as placing bread into toaster or opening a lid. Here we see Miles performing 4 tasks in the presence of distractors, where in each video shown in this slide, across its evaluation run, the distractors are randomized in the scene, as well as the pose of the object with which Miles is interacting with. So here we can see, for example, opening the lid or inserting a plug into a socket. As shown, Miles is quite robust to the presence of distractors and can handle big variations in pose changes of the object. Here we see Miles' generalization performance after having been trained on the 5 bins shown on the left and generalizing to the 2 bins shown on the right, where Miles has to pick up a marker and place it in the bin. As shown, Miles can generalize to both differences in color and shape of the bins. In this slide, we overview the performance of Miles against 4 baselines evaluated over 20 trials on 7 everyday tasks. We evaluate Miles against 1 baseline that just replays a demonstration with no learning, 2 baselines that leverage a single demonstration and reinforcement learning to learn a policy, and 1 baseline that performs post-estimation followed by demonstration replay. In this case, no method used any environment resetting during the data collection process for a fair comparison. As we can see, Miles significantly outperforms all the baselines. Thank you very much for watching the video. You can find more details about Miles on our paper and our website. Thank you.